Swayam Prabha. Digital India. Educated India.
Hello, this is the third week of lectures of the course on compliant mechanisms, principles and design. Last week we looked at flexures as well as finite element analysis used to analyze compliant mechanisms, which primarily consist of elastic beam segments or what we call elastic elements. And we emphasized nonlinear analysis, in particular geometrically nonlinear analysis. And we saw that finite element analysis can simulate just about any compliant mechanism, whatever the nonlinearity might be, but then it is not so useful for design purposes always, and usually getting some useful insight is also difficult with finite element analysis. If we have an analytical solution, it will be much better, which is what we will do this week, trying to get the insight into large displacement analysis of beams, in particular with cantilever beams. So, let us begin by looking at a cantilever beam and how it behaves when it undergoes large displacements under very large transverse loads. So, looking at the cantilever beam, we had seen this picture in the last lecture, where if someone shows a cantilever beam deformation when there is a load, transverse load at the free end, how does it deform? We have shown both linear and nonlinear. How do we tell them apart? We had said that if we actually observe by looking at whether there is displacement in the axial direction, as the loaded tip starts moving, it is going to have displacement not only in the transverse direction, that is this direction, but there is always also displacement in the axial direction, that is this direction, which happens only in the nonlinear case, but not in the linear beam theory case. Okay. And now today we are going to discuss this nonlinear displacement in detail analytically. So, let us recall the assumptions made in the linear beam theory, where we are all familiar that we will have Young's modulus E, moment of area I, second moment of area I, and then there is this W double prime, that is second derivative of the transverse displacement W x with respect to x, and this is our bending moment. This is what we call Euler-Bernoulli theory, where we say that this particular quantity that we have W double prime is actually an approximation of the curvature. This is an approximation of the curvature. So, curvature, which is inverse of a reciprocal of the radius of curvature, where this is curvature, where rho is the radius of curvature, which is given by W double prime plus divided by 1 plus W prime square raised to 3 over 2. Now, when we say it is an approximation, we are neglecting this W prime. So, for a small displacement which will entail only small rotations, hence W prime, which is dW by dx, when a beam deforms like this, if I draw a tangent, this will be the slope theta, that is W prime dW by dx. When that is small, that is bending is limited, then we can neglect this, then this approximation by W double prime is valid. That is one assumption we had made in linear beam theory. Other is more subtle, is this bending moment. We write bending moment in the original configuration. If I have a beam like this, since we are discussing cantilever beam, let us consider that when I apply a force anywhere, but in our case we are going to apply the load at the free end, transverse load. We write bending moment diagram in this configuration rather than in the deformed configuration. So, we saw that in the case of nonlinear analysis, there will be a transverse displacement, we can call it WL, as well as UL, which is in the axial direction. It is not the axial deformation in the sense of stretching of the beam, it is just that the locus of this will have both components, transverse component as well as the axial component. And you have to write the bending moment in this deformed configuration rather than the original configuration. That is the difference, and also the assumption that we make in the linear analysis is that bending moment or equilibrium written in the original configuration is good enough, but that is not good enough in the case of nonlinear. So, the two differences which we just discussed are apparent here. You can see this is the linear case that we just discussed, and this is the nonlinear case that we are going to discuss now. And you can see that d theta by ds, which is nothing but the curvature, how the slope of the beam is changing with respect to arc length parameter, that is to be noticed S. So, if the beam is like this, we measure S along the bent profile of the beam rather than original one may be like this, that will be x, whereas this is S, and d theta by ds is the curvature. So, we had an approximation here, now here it is not there. The other is, if we look at the bending moment, this is in the original configuration. So, that simply f times L minus x, but here we have additional, which we said is UL. If the beam were to be like this when it is bent, what is this displacement UL at the x equal to L or s equal to L. Okay, that is what we have. Okay, these are the two differences between the linear and nonlinear governing equation. So, this is the equation that we need to solve now, and you can see that this equation involves d theta by ds, which as we saw is nonlinear because there is w double prime divided by 1 plus w prime square raised to 3 over 2. So, it is nonlinear, and we have this extra variable UL. So, we have a differential equation to solve for w of x, but we also need another equation to solve for the scalar UL. So, we need another scalar, which we will see as we go along. These are the three important references for this content of this lecture. You can look at the dates. 1859, Kirchhoff, the same Kirchhoff of circuit theory, and who had also worked on plates. He had worked on this infinitely thin bar, people used to call it a bar, now we call it a beam, on the equilibrium and movement. So, he had done some fundamental work, we will refer to what he had done. And Bishop and Drucker 1945, they had looked at these large deflections or displacements of cantilever beams. Much of what we discussed today is from this paper, and they had done this analysis in the context of analyzing the fishing rods, which are very flexible, and they needed to analyze, I guess they did for in that context. And there is this beautiful book called Flexible Bars written by Frischwey, and this book is a comprehensive set of chapters that deal with various beams and under various loading conditions. So, these references will be good to use to understand more than what we will discuss in today's lecture. So, once again these are small displacements that we have and a large displacement governing equation with a tip load, that is all we are taking, and we have this UL appearing in the large displacement case in addition to W of x. This equation is called Elastica equation, not elastic, Elastica equation. The solution of this will be called an Elastica. So, we have E I d theta by ds equal to f times L minus x minus u L. If we think about how we might solve, there is a clever technique that Bishop and Drucker and others have found. So, I will explain it in simple steps, so we can appreciate what they had done. So, we have a differential equation and also we have a scalar unknown. So, our unknowns are w of x as well as u L, two unknowns, one function, one scalar. So, we have a differential equation, so function is taken care of, but in another scalar equation to solve for u L. We are differentiating with respect to s, okay, the arc length parameter. So, that becomes d theta by ds. I have taken E I the other side. So, f over E I with a minus sign because this is minus x, this becomes dx by ds. Okay. And we also note that this dx by ds is equal to cosine theta. So, when a beam deforms like that, if I take this element and small element, infinitesimal element that call it ds, then there will be a vertical and horizontal component. We are here interested in this horizontal component dx, that will be ds then cosine theta. So, we are replacing the dx by ds with cosine theta. Okay. And then we do now see the analogy between the large displacement oscillations of a pendulum. This is Kirchhoff's pendulum analogy and equation that we got. So, we have second derivative d square theta by ds square, here d square theta by dt square, that square I forgot. So, dt square, and then we have cosine theta here, sine theta, that does not matter because if I draw the pendulum, normally we denote this angle as theta, instead I can denote this angle as theta, that becomes cosine theta what we have here. So, you can see that the large oscillations of a pendulum and the deflection of a beam are governed by the same mathematical equation. Does it mean then that there are some oscillations also in this beam? When you take a cantilever and apply a load, it is a static equilibrium equation. Where are the oscillations? Turns out that there are indeed oscillations if you extend it a little further. Let us say I take a long beam and bent it into a form like this. Imagine that there was a vertical beam, we will come back to that later. We applied two loads, that is I have taken a beam, we buckled it basically applying two loads, right. If it buckles both sides, it is going to become something like this, and this one if beam were to be longer, it will actually go like this. So, this undulating elastica, that what it is called, undulating elastica. Elastica is the deformed profile of the beam. It is undulating, meaning oscillations, just like the oscillations of the pendulum that undergoes large traversal. So, this normally we study small displacements, in which case sin theta is approximate as theta, then we can solve it easily. Now, when there is sin theta as it is, which cannot be replaced with theta, then it is a nonlinear equation that will have a feature that we are seeing here right now. But one thing to remember, even though we are calling undulating and talking about oscillations, what is oscillating here? It is a tangent. If I take a tangent at every point along this path of the beam that is very long and we have buckled it into shape by applying forces, this tangent will be oscillating. That is the explanation that we can give, but let us understand that when two different systems are governed by identical mathematical equation, it does not mean that always the physics of the two is the same. Here the physics is entirely different. There is inertia for this term here for pendulum, here there is no inertia because it is a static model, yet the equations are the same, but physics is different, but there are oscillations in this undulating elastica if extend it a little further. Okay. Now, coming back to the equation, we just took a detour to talk about Kirchhoff's analogy for the beam that we got now. Now, let us proceed by doing a little manipulation. D square theta by ds square that we have, we multiply by d theta by ds on both sides. of the equation, and then we integrate now in order to get half d theta by ds square. If I take derivative, I get back this one. On the right hand side also we have integrated. Now we have a constant c. That c, how do we evaluate? We use the fact that at the free end of the beam, when a cantilever beam deforms like this, at the free end moment is 0 and hence curvature is 0. Curvature is 0 means that d theta by ds at s equal to L is equal to 0. So, that means that f by EI sin theta L plus c is equal to 0. That gives us that c to be equal to, there was a minus sign here, notice that there is a minus sign that came from the differentiation. So, c equal to f by EI sin theta L. So, we got an equation now which is of the form I can write d theta by ds equal to minus f by EI sin theta, and then we also have f by EI sin theta L, and then 2 goes here, this one, and then 2, and we have to take a square root because it is d theta by ds square. We got an equation. So, we got an equation that transformed from here to here. Now, in the process we have managed to eliminate that UL that was there, but we need an equation to solve for it, as we will see later. So, let us proceed with this equation that we have, d theta by ds is 2f by EI. I have just taken it common, sin theta L minus sin theta. Okay. Now, we bring in that, we eliminated that UL, but we still need an equation to solve for that extra scalar that we have UL. So, we use this assumption of no stretching of the neutral axis of the beam, which is to say that if I integrate from 0 to L along the arc length parameter ds, I will get the full length L. There is no stretching, there is no contraction. Since we have this d theta by ds, we can take ds other side, bring this downstairs. So, what we have is this equation that is equal to L. So, if you notice what we have done now, this is a scalar equation because this is just a one equation. What we have here is a scalar equation. So, the unknown in this should be also a scalar, which is this theta L, because once you integrate from 0 to theta L, this quantity that is going to have only theta L, it is a function of theta L. So, we have a function of theta L is equal to L is the equation that we got. So, even though we had differential equation, by using this couple of tricks we managed to get an equation in one variable. That is a highlight of this method. How do we solve this? Well, before that I have just put into slightly different form. Let me erase a few things that I have written, so you can see the equation better. So, what we have here is the same thing written slightly differently by defining a non-dimensional quantity denoted by eta. It is a non-dimensional quantity which is a very important parameter in this analysis. You see non-dimensional because force has newtons, and then this is meter square, and then E is Newton per meter square, second moment of area is meter to the 4. So, it is non-dimensional, we can see it, right. So, Newton, this is m2, this is m2, no dimensions, right. So, what you have here on the left hand side is actually a non-dimensional because it only involves the angle theta. Okay. Now, how do we solve this? This is the equation that we have at this time. How do we solve it? In order to solve, we use change of variable. We are changing theta to another variable called phi, and these are the equations that we are using. So, sin theta is 2 p square sin square phi minus 1, and then p square 1 plus sin theta L by 2. So, there are two change of variables, I should say, theta to phi and then theta L to something called p, which is called the modulus of an elliptic integral that we will see. Actually, we have it right here. So, this is an elliptic integral of the first kind. This is an elliptic integral of the first kind. So, we are using two change of theta to phi and theta L to p, which is what are indicated over here. And let us see how this thing comes from here, how we get here, we will try to figure that out. So, first let us look at the limits. When we change theta to phi, when I take the case of theta equal to 0, this implies that that is sin theta, which is 0 from here, equal to 2 p square sin square phi naught, let us call it, minus 1. That means that phi naught, the lower limit, is going to be 1 over 2 p square under square root, and then it is actually sine inverse of that. So, let me put sin phi naught here and then say phi naught is sine inverse of square root of 1 over 2 and then p square. I can take p outside, does not matter, that is phi naught. And what happens when there is theta equal to theta L, which is the slope at the loaded tip? When you have that, then we can go back here and then see what it is. So, we can see that we have I think it will be one of these. So, we can see that when theta equal to theta L, when we go back to this first equation itself, sin theta L, that is this equation, equal to 2 p square sin square phi minus 1, and then we know sin theta L from the second equation is 2 p square minus 1, and this side we have 2 p square sin square phi minus 1. So, now minus 1 gets cancelled, 2 p square gets cancelled after that, then we get sin square phi equal to 1 or phi equal to pi by 2. It can be 3 pi by 2 and so forth, but we take the first one, this undulating elastic curve, we take in the first instance of that. So, we have our limits from phi naught to pi, this is our phi L. Okay. So, having done that, now let us look at further of converting this to the new form. There are two steps here. One is we have the first equation which I am showing here, sin theta is 2 p square sin square phi minus 1. Let us differentiate it in order to replace d theta to d phi. So, we have first taken this equation, differentiated with respect to theta, cosine theta times d theta, 4 p square sin phi cosine phi d phi, and cosine theta is written as square root of 1 minus sin square theta, and then right hand side remains the same, and then sin square theta we substitute this equation for sin theta. So, 2 p square sin square phi minus 1, square it, and if you simplify you will get this to be that one, 2 p sin phi times square root of 1 minus p square sin square phi d theta, right hand side remains the same. You can see that sin phi is there and 2 p that gets cancelled, then we get d theta. When you replace, you will have to put d phi and then this quantity 2 p cosine phi divided by square root of 1 minus p square sin square phi. And let us also look at, let us separate it out, sin theta L, because we also want to replace this in terms of phi, right. So, sin theta L is 2 p square minus 1, sin theta is 2 p square sin square phi minus 1. If I take the difference of these two, then I get this sin theta L minus sin theta becomes, the 1 gets cancelled, then we will get this 2 p square times 1 minus sin square phi, and then 1 minus sin square phi square root was there. So, it becomes square root of 2 p cosine phi. Okay. Now, both of these results we substitute over here and the limits also we calculated. Let us see what we get. So, when you do all this with these two things that we did in the last slide, when you substitute over here, we get, and the limits that we did, sine inverse 1 over p square root of 2 to pi by 2, and then d phi divided by 1 minus p square sin square phi is equal to eta. We have taken this 2 also the other side. This square root of 2, the square root of 2 will cancel. Cosine phi that is there here, this goes to denominator, that goes to numerator, they all cancel. Finally, we get this one. Now, have we solved the problem? In fact, we have, and that is because what we got here is what is known as the elliptic integral of the first kind, incomplete when it is something less than pi by 2, the upper limit. When it is pi by 2, that is called the complete. These elliptic integrals are very important in mathematics for many reasons. They first arose in terms of computing the arc length of an ellipse. Circle, we know how to do it, simply r times theta, but for an ellipse it involves this equations. If normal trigonometric functions are called circular functions, the corresponding functions for an ellipse are elliptic functions. Related to that are these elliptic integrals. So, we have these equations of the first kind. When what is the denominator goes to the numerator, that becomes an elliptic integral of the second kind, again incomplete and complete. We have a third kind which we do not need in this particular context. So, we actually have a solution now, because we converted the differential equation that we had and that scalar equation UL with the no stretching assumption, we convert it into an equation that looks like this, where this eta, which involves force, length, Young's modulus and second moment of area, all of these things are captured in this eta here. If I know eta, they can compute here the value of p, that is called the modulus of the elliptic integral, and the p as we know is related to theta L. So, I can get this theta L for a given value of force. How is it useful? In fact, we have found theta L. When we have theta L, we can get the other ones as well. What are the other ones? We want to find out what this WL is and what this UL is. So, for both of these, we have now the F denotes of elliptic integral of the first kind, complete, this is incomplete, this is second elliptic integral, complete, and then incomplete, because this phi naught is there, and UL involves only this p and this eta. So, we are able to get them at the free tip. We can also get everywhere in between, as we will see now. Let us see how this works. For transverse displacement, as we already saw, that if we have an arc, if this is ds, then this vertical part is the transverse displacement dw. This is dw, this is dx for that segment. So, dw is since this is theta, this is sin theta, ds sin theta. We take the dw and we substitute for this ds from this equation. So, ds that we have, this will be ds goes that side, d theta divided by this, and then you have sin theta which has appeared here. And we had just done how to change variables from d theta to d phi. So, d theta we substitute this whole thing in terms of d phi, change of variables, and likewise we have this other equation, square root of sin theta L minus sin theta, which is square root of 2 times p cosine phi, substitute, we get something like this, and we cancel a few things, p cosine phi, square root of 2 here, square root of 2 here, with that 2. Okay. So, we cancel those, we are left with this thing. Okay. And we also note now that this sin theta that we have over here, that can be written also in terms of what we already know. This is what we got in the last slide. The sin theta is 2 p square sin square phi minus 1. So, I substitute for sin theta this quantity over there. Then we do a little manipulation, we add plus or minus 1 to this, we add a minus 1 and a plus 1. Why do we need to do that? If I add minus 1, this becomes 2 p square sin square phi minus 2. I can take 2 outside, that becomes square root of 1 minus p square sin square phi, because in the denominator there is the same quantity 1 minus p square sin square phi, and the plus 1 gives rise to this one, just 1 by this one. So, this is minus 2 times 2 p square sin square phi minus 2 or 2 times p square sin square phi minus 1, and 2 is here with a minus sign. Since there is square root of the same quantity downstairs, that becomes square root of 1 minus p square sin square phi. Now, if you notice, what we have really is elliptic interval of the first kind here and then the second kind here. Okay. So, that is why with the limits put in from phi 0 to pi by 2, we get W L by L. I made it non-dimensional here by dividing by L throughout. So, that is why here I get eta, because eta is f L square by E I. In fact, it should be 1 over eta. So, minus 1, okay, E I by f that we have here. So, that is what we get, and then we have this p and then phi naught, which all depend on the theta L, the endpoint displacement. So, we are able to do the W L there. In order to do axial displacement, that is U L, we had written that expression earlier, that basically comes from this equation that we can do at theta equal to 0. So, if I do that, that E I d theta by d s at theta equal to 0, I will have f times L, x is 0, U L, we need to find U L, and then we see what is d theta by d s, the theta equal to 0, which we have, sin theta is 0, then I can put that as E I into square root of 2 f by E I into sin theta L, because sin theta is 0, that is equal to f times L minus U L, and then we further note that theta L is in terms of this 2 p square minus 1, 2 p square minus 1 sin theta L, we substitute, we get what is written there. So, we get U L as well here. So, we can plot them. So, we have this non-dimensional quantity eta here, and on the y axis we are showing W L by L, also U L by L, the transverse and axial displacement of the free end or loaded tip, and we are also showing the linear one here, that is a line, that will be this is like a force displacement, rather we have interchanged the axis, displacement here and force on the x axis, we have a straight line, that is a linear one, and this eta has gone as far as 120, and we can see how W L by L, U L by L vary, and you may wonder whether the slope of this curve, the dotted blue line, how come it has a finite slope? In fact, it does not, it has a 0 slope at the origin here, because linear analysis will not show you any UL. So, it should have 0 slope coming there. In fact, if we take a close up view of that, we can see that it actually has a 0 slope and then it turns like that, okay, that is taken care of. All right. Now, let us also look at how theta L varies with this eta, and as you can see, as eta increases, theta L is increasing, approaches 90 degrees in the limit. So, if you take a cantilever beam and apply a large load, eventually it can go to almost 90 degrees, okay, that is what is shown, but for that we need to go for a very high value of f, f L square by E I together. Let us call this theta L then the index of bending. The larger theta L is, larger the value of eta is, the larger theta L is, it indicates how much the beam has bent. And let us also compare this with finite element analysis, because we discussed non-linear finite analysis at length in last week. Let us see how close it is. It looks like the two dots, the blue dots we have for two things, they seem to be lying right on the curve, but if we actually take a closer look at that, then actually they are not, there is a discrepancy, right. So, which is more correct? Clearly non-linear FEA is more correct than analytical one, because analytical one had made an assumption that the neutral axis does not stretch, the beam does not stretch, but in reality it would, because if I take a beam and when it deforms, when my loading is vertical like that, there is a component along the beam. Not only in the beginning it is not there, that is why linear does not show, but it deflects, load continues to be the same direction. There is a component there, component here, one bends, other stretches a little bit. Of course, axial stiffness will be very high compared to bending stiffness. There will be a rate of stretch which is not taken into account in the analytical one, and hence analytical one, which is our curve, deviates a little from the finite element analysis. Okay. Now, if I want to plot the loaded tip, let us say I have a beam like this, we calculate W and UL for varying values of forces, I can get this locus, and we will be talking about this later on. And if I want to get this deformed profile, this method does allow. If you remember, we had this dw and then integral in terms of d theta, which we convert later to d phi, right, we did that. So, we did this from 0 to L completely, but if you do partially, then you will get that displacement if you change 0 to, instead of pi by 2, something less than pi by 2. If you do, then you will get this transfer displacement everywhere. Similarly, you can do that for du also. So, you will know this value at different points. So, you can get the entire beam different things, that I leave it as an exercise for you to do. So, let us now capture the important steps in what we discussed today. We started with this equation, and also we had that ds equal to L, those are the important equations. We first differentiated and then did an integration after little manipulation to reduce to one equation involving only slope at the loaded tip, and then we did this no stretching assumption, which is that to solve that theta L, solve for the theta L, and then we reduced it to elliptic integral of the first kind, and that we assume that these elliptic integrals cannot be solved in terms of elementary functions or analytically, but numerically you can do that. There are a lot of routines in MATLAB and other software to get this. So, we have reduced that thing to a numerical solution in one variable involving elliptic integrals, and finally, we also saw how to get transverse and axial displacements of the free tip, and also we can get for any point on the profile of the beam. So, you can get the entire deformed profile. And some more things that we need to note for later lectures is that this non-dimensional quantity eta has a lot of significance. We call it index of bending, and then the analytical solution that we got lets us draw this locus of the loaded tip, which has very important implication in what we will discuss in later part of this week's lecture. And one more thing that we will also look at is the geometric interpretation of the change of variable. It is not just a mathematical convenience, this phi plays a very important role in solving other beam problems, cantilever beam with multiple loads, or a vertical beam like a column buckling, and also beams under different boundary conditions, fixed and so forth, which we will revisit by describing this geometric interpretation of the change of variable. Thank you.